Hello students, this is lecture number 23 and lecture number 24 which is about infinite impulse response filters, or in short IIR filters. In last lecture, in lecture number 21 and 22, we discussed about FIR filter and different design methods of FIR filter, and now we are going to discuss about the IIR filters. So IIR filters, as I told you, are infinite impulse response filters, and they are generally chosen for applications where linear phase is not very much important, right? And the memory available on board is limited, right? You need less number of computations on board, so basically it is a cheaper implementation of any filter, right? So as far as the magnitude response is concerned, it's good, but their phase response, it's not generally linear. So comparatively in FIR filters, the phase response was better. It was linear, perfectly linear, as we will see in coming slides. I will show you the comparison between the phase response of IIR filter and the FIR filter. And the advantages of IIR filter are low implementation footprint. Right? It requires less memory, less number of coefficients as compared to the FIR filter for same specification. Right? If you want to design a band pass filter, having minimum transition band and all these requirements, then the IIR filter that fulfills the requirement would require less memory as compared to the FIR filter. However, the phase response won't be linear. And also, in those applications where low latency is required, IIR filters are more suitable. Now, IIR filter can be represented by the equation shown here. You can see this difference equation. Now, this is exactly same equation if we ignore output terms, right? If we ignore output terms, this equation would become the equation of a FIR filter, because in FIR filter there is no feedback, and in IIR filter there is feedback. So they are represented by a difference equation having input terms and output terms, right? So output in IIR filter is basically linear combination of input and output terms. It can also be represented in this form. It is a short representation of the same difference equation. So here input terms, number of input terms are P and number of output terms are Q. Because of the feedback, this filter is also called a recursive filter, right? Because it has a feedback, and it is also an auto-regressive moving average filter, right? Auto-regressive moving average filter means that it calculates the average of linearly combined input and output terms, right? And it moves along in real time, right? So this is the difference equation, and if you want to compute the transfer function, which is also called the pulse transfer function, we know the transfer function is ratio of z transform of output upon z transform of input. So if we will take z transform of this difference equation and separate the input output terms and we'll compute the ratio, you will get this transfer function, right? So you can see there are q number of poles and p number of zeros in this equation. So output y of n of the filter can also be represented by a convolution sum, right, where h of k is the impulse response of the filter, which can be determined by taking the inverse z of this, and x of n minus k is the folded and shifted version of input. Now the transfer function of the system can also be written in this form, right? H of z equal to z transform of h of n, right? Impulse response of the system, and the frequency response of the system can be represented by the Fourier transform summation h of e power j omega equal to n 0 to infinity h of n and e power minus j omega n. Now here in all these summations we are using n equal to 0 to infinity, not minus infinity to infinity, because we are dealing with the causal systems now. When we talk about filters, we talk about causal systems. Now and there are various design methods for IIR filters, and the most common ones are where we already have an analog filter and we want to implement it digitally. Then we have some conversion methods that are used to convert the analog filter into the discrete time filter or digital filter, and other direct design methods are also available. But since the design methods for analog filters are very well established, therefore commonly this approach is used for design of IIR filters. And in this lecture we are going to discuss about these three methods, and we'll use these three methods to design different types of IIR filters. One of the method is impulse invariance method. Then second one is approximation of derivatives, which is also called backward difference. And the third one is the bilinear transformation. It is also called Tuston's approximation. So first we'll discuss about the impulse invariance method. Now in impulse invariance method, we have three steps in conversion of analog filter design to the digital filter. First we'll compute the inverse Laplace transform to get the impulse response of the analog filter, right? So we'll be given a transfer function in terms of s, in s domain, in Laplace domain, because analog systems are represented in s domain. So we will be given the transfer function of the filter in analog domain, in s domain. So in order to find out the impulse response in time domain, we will compute the inverse Laplace, and then in second step we will sample the impulse response of the system, because impulse response obtained in the first step would be a continuous time impulse response, and in order to convert it into the discrete form we will sample it, right? And we have to choose sampling frequency wisely, so that we have to avoid the aliasing problem as well. Then in third step we will compute the Z transform of the sampled version of the impulse response, and you will get the transfer function of the system in terms of Z or in discrete domain, which is also called the pulse transfer function. So let us start with an example. In this example we are given a low pass filter which is analog filter and has the cutoff frequency 3 radian per second, and let us convert this transfer function into digital IIR filter using impulse invariance method. Now this transfer function, the analog transfer function, is also referred to as the prototype, low pass filter prototype. In some books or on internet, if you will search for this, usually the authors refer to this transfer function as the analog prototype. So this method is also called the conversion of analog prototype into digital form. So this analog model is given here, and we have to convert it into the digital by impulse invariance method. So first step is to compute the inverse Laplace transform of this transfer function. So we can rewrite this transfer function in this form. Now the inverse Laplace of this is 3 exponential minus 3t, right? Now let us sample this transfer function by substituting t equal to nt. You will get h of n equal to 3 e power minus 3 nt, right? So now this is the discrete version of the impulse response. Now we can find out the Z transform of this function, and the transfer function that you will get would be the pulse transfer function. Your filter would be converted to digital form, and then you have to choose the value of t, right, depending using the sampling theorem that you already know, that should be low enough that to avoid aliasing. Now we can use Laplace transform and Z transform table to compute the Z transform. You can see here the Z transform of exponential is z upon z minus whatever the exponential is, right? So Z transform of this function would be 3z upon z minus e power minus 3t, because 3 is constant and e power minus 3 and t. The Z transform of this function will be z upon z minus e power minus 3t. Right. Now if we plot the frequency response of the filter, this one is the analog one and this one is the digital one, and you can see that this is the cutoff frequency, which is 3 radian per second, and this is the 3 dB bandwidth. So you can see that approximation is good, and we have almost similar type of frequency response. The magnitude response, only difference is in the gain of both magnitude responses. So gain doesn't matter, we can add the gain to the system, but the basic characteristics, the cutoff frequency is same. And now here we have actually considered t equal to 0.1 second. Now as far as the phase response is concerned, it is quite nonlinear, right? You can see that the phase, it has a huge phase shift near the corner frequency, near the cutoff frequency, and because of this nonlinear phase, the problem may arise in real time. Now let us compare this phase response with low pass FIR filter. So in this figure you can see this is the phase response of low pass IIR filter having cutoff frequency 3 radian per second, and this is the phase response of low pass FIR filter with the cutoff frequency 0.55. So this is the pass band from 0 to 0.55 for this filter, and this is the pass band from 0.1 to 3 radian per second for IIR filter. So you can see it is not quite linear, although it can be, it is acceptable, but it's not linear. But the phase response of FIR filter is is like a straight line, it's very linear. So as far as the phase response is concerned, we can say the FIR filters are better, but of course it is always there is always a question of design trade-off, whether you need to implement this cheaply on a cheap board like Arduino or something like this, or you need a FPGA board to implement FIR filter. That is always a design trade-off and depends upon application, what is the requirement. Now the phase response is important. Magnitude response of course is important, right? But the phase response is important because when the phase varies linearly during the pass band, then all the frequencies are delayed by same amount of time at the output, right? This is what we call it a group delay. So the group delay of the filter is same. So therefore the phase distortion is minimum. But when the phase response is not linear, then some of the frequencies are delayed longer than the other frequencies. For example, here you can see the delay is proportionally higher than the delay here. So group delay is not same, it's different, therefore the phase distortion occurs. So in IIR filters you can expect phase distortion at the output in real time, but in FIR filter it is minimum. Now example number 2, we are given a band pass analog prototype with the transfer function given here, and we have to convert it into the digital one using impulse invariance method. So in the same way, we can convert it. First we have to find out the inverse Laplace, and inverse Laplace can be determined by, obviously we have to now break it into the partial fractions, because direct determination of the inverse Laplace is not possible. So after breaking this into the partial fraction, you will get these two residues, and inverse Laplace of this would be exponent of minus of this multiplied by t, and similarly plus 1 upon 2 e power exponent of this minus t. Now we have the impulse response of the filter in time domain. Now we have to sample it. So substitute t equal to nt in this. So substituting t equal to nt, we have now discrete version of the impulse response. So now we can directly find out the z transform using the z transform table, right? So again we have exponential function here. So we know that the z transform of exponential is z upon z minus whatever the exponential is, or 1 upon 1 minus z minus 1 multiplied by exponential. So after simplification, you will get this transfer function. This is the discrete time or digital transfer function of the band pass filter. Now we have to compare the magnitude responses in analog version versus the digital version. You can see here that the magnitude response are quite similar. Here the resonant peak is quite higher than this one, and the bandwidth is narrow as compared to the analog one, but the center frequency, the resonant frequency, are almost same. There is slight shift in the resonant frequency, if you can see here. Otherwise, it's a quite good approximation at t equal to 0.1 seconds. So what I would suggest you to change the sampling interval and see what kind of effect it has on the amplitude response. As far as the phase response is concerned, it's quite terrible. You can see that phase response around the corner frequency is dropped to 180 degree. It has 180 degree phase shift at the output at the resonant frequency. So this could cause a huge problem in real-time implementation. There will be a huge phase distortion in the output. So if you are implementing this for a sensitive application, it's not a good way to implement a band pass filter. You probably should use the FIR filter instead. Now the high pass filter, the transfer function of high pass filter is 1 upon omega c upon s plus 1, where omega c is the corner frequency. So in low pass filter, when we substitute s equal to 1 upon s, it becomes high pass filter, right? So instead of s, we have substituted 1 upon s, so we get the high pass filter transfer function. Now in the same way, we have to break it into partial fraction, because direct determination of Laplace transform is not possible. So the partial fraction expression of this function came out to be 1 minus s upon s plus 3. Now the problem is inverse Laplace of 1 is direct delta function, which is impulse function, and the inverse Laplace of this is 3 e power minus 3t. Now sampling of delta function is impossible, because it is a single, it only appears at t equal to 0. So sampling of this is not possible. Therefore this method cannot be used to design high pass filters or those transfer functions which are strictly proper. Strictly proper means the numerator polynomial and the denominator polynomial has the same degree. So in such conditions, usually what happens that we have a constant in partial fractions like here, right? So whenever such condition appears, we won't be able to sample the impulse response of the filter, right? Because of this impulse function here, it's impossible to sample this. So I would say that this method is not suitable for high pass filters and for those filters in which transfer functions are of this form, right, where when we take in partial fractions, a constant appears in the partial fraction expression. So the presence of delta term prevents sampling of impulse response, which thus cannot be defined. So fundamental problem: high pass and band pass filters have functions with numerator and denominator polynomial of the same degree, and thus cannot be designed using this method. So those transfer functions which have numerator and denominator polynomial of the same degree, and in their partial fraction expression there is a constant, then this method cannot be used. So in general, the advantages of impulse invariance method are: preserve the order and stability of the analog filter. It preserves the order and the stability. The order of the converted filter remains whatever the order of the analog filter was, and stability is also preserved. If the analog part was stable, then the digital part would be stable as well. What are the disadvantages? Not applicable to all filter types. Usually high pass and band pass filters have strictly proper transfer function, and it's not applicable to those types, right? So not in all cases, but in some cases it is not applicable. There's distortion of the shape of frequency response due to aliasing, and there because we have to sample the impulse response, and if we do not choose the sampling frequency properly, there may be some aliasing in the frequency response. The second method, which is called the backward difference method, is also used to convert the continuous time or analog filters into the digital filters. In analog domain, variable s represents differentiation, right? If you remember, d upon dt is basically s in Laplace domain. So what we do, we can approximate s by differentiate operator in the digital domain. For the derivative at time equal to nt, we substitute backward difference as dx of t upon dt equal to x of n minus x of n minus 1 upon t. So this is basically the backward difference. Backward difference means current sample minus the previous sample. There is also approximation like forward difference, in which we have x of n and the next sample, right? But forward difference, of course, is not causal, so therefore it cannot be used in real-time applications or filter approximation, right? So we use only backward difference. So backward difference is current sample minus the previous sample divided by the sampling interval, right? So this is a numerical approximation of continuous time derivative. Now we know that y of t is suppose y of t is equal to dx of t upon dt, then the Laplace of this would be y of s equal to s into x of s, right? So d upon dt is simply equal to s, and d upon dt in discrete domain is equal to x of n minus x of n minus 1 upon t. So we can say s is equal to x of n minus x of n minus 1 upon t. So y of n is equal to this, then y of z equal to x of z minus 1 x of z upon t, and taking x of z common from here, you can say 1 minus z minus 1 upon t. So this is the derivative in z domain, and in Laplace domain y of s is equal to s into x of s, right? So s is basically equal to 1 minus z minus 1 upon t. So s is derivative in Laplace domain, and 1 minus z minus 1 upon t is the derivative approximation in z domain. Now this figure shows the mapping of s-plane poles onto the z-plane poles when we use backward difference approximation, in which s is equal to 1 minus z power minus 1 upon t. The t is the sampling interval. Now you can see the entire left half plane of S domain, which is the stable region, is mapped onto a circle of radius 1 upon 2 and the center also 1 upon 2. So entire stable region is mapped into a very small area in Z plane. Right? So this becomes problematic when we have to design the high pass filter and some band pass filter with higher frequencies using this technique, because we cannot map all the frequencies which are represented in S plane onto this circle using this approximation, right? So as a consequence, the this technique is suitable for low pass filters and some of the band pass filters, and of course not suitable for uh, high pass filters. So band pass filters also only those band pass filters which have some relatively small resonant frequencies. Now example 4 is basically same as the example number 1 we solved using impulse invariance method. Now let us convert this analog low pass filter using the backward difference approximation, right? So in this method we'll substitute s equal to 1 minus z power minus 1 upon z into the analog transfer function. So this would give you the discrete time or digital or the pulse transfer function. So h of z equal to 3 upon 1 minus z power minus 1 upon t plus 3, and after some simplification you can get the transfer function in this form: h of z equal to 3tz upon 1 plus 3tz minus 1. So here you can see the choice of t plays an important part, which is the sampling interval, right? So it depends what sampling interval you choose. For example, if you choose capital T equal to 0.1, then the 0 of the transfer function would be 8 minus 0.3, and similarly the location of the pole would also depend upon the choice of capital T. So this figure compares the magnitude responses of analog and digital filters designed using impulse invariance method as well as the backward difference method. So you can see the cutoff frequency is 3 radian per second, which is quite you can see same in all three cases, and there are no significant difference in shape of the magnitude response. However, there is some difference in the gain. Here you can see the gain is a little bit higher. Otherwise, the shape of the frequency response is more important, because in digital conversion aliasing occurs, and in any case if there is aliasing, then that is not a good approximation. So shape of the frequency response is same in all three cases. Then the next example we solved using impulse invariance method was this band pass filter. So let us now use the backward difference approximation to design or convert this analog band pass filter into digital band pass filter. So similarly, you will substitute s equal to 1 minus z minus 1 upon t in this transfer function. So first let us simplify this transfer function and then substitute backward difference. After substituting and simplification, you can get this transfer function h of z equal to this. It has two zeros and two poles now, right? You can see one 0 is at equal to 0, other 0 it depends upon value of t. similarly it has two zeros here. So if you compare the magnitude response, now you can see that the magnitude response of filter, the digital filter converted using backward difference, has almost same type of magnitude response as the analog filter. However, the resonant frequency is shifted towards a higher frequency in case of impulse invariance method, right, for same value of t. So we can say that as far as the low pass filter design is concerned, you can use either impulse invariance method or the backward difference method. However, when we have a band pass filter design, you know having low resonant frequencies, we can prefer backward difference approximation over impulse invariance method. Then the third type of approximation or the method that is used to convert analog filters into digital filter is the bilinear transformation method. This method is most widely used, which is suitable for all three kind of filters: low pass, band pass. In fact, all four kind of filters: low pass, high pass, band pass, and band stop filters. So this type of approximation is also called Tustin's transformation, right, or Tustin's approximation. So in this approximation, S is basically equal to 2 upon T and 1 minus Z power minus 1 upon 1 plus Z power minus 1, or S equal to 2 upon T, Z minus 1 upon Z plus 1. So now starting with the same example that we did in previous two methods, a low pass filter, and in this filter let us substitute S equal to 2 upon T Z minus 1 upon Z plus 1. After substituting, you will get this digital transfer function h of z equal to 3t z plus 1 upon 3t plus 2 into z minus 2 minus 3t. Now if you compare the magnitude responses, you can see that as far as the magnitude response, shape of the magnitude response is concerned, till the pass band there is no difference, right? So you can use any of the technique. There's it doesn't matter. Then the next example is the band pass filter. So let us substitute s equal to this value into the transfer function, and the transfer function that you'll get is now second order. It has two poles and it has two zeros. And if you compare the magnitude response, you can see that the in bilinear transformation, the shape of the response is quite close to the shape of the response of analog filter. However, there is a slight shift in the resonant frequency which can be ignored, as compared to the impulse invariance method. The backward difference and bilinear transformation has slight shift in the resonant frequency, very slight shift, which is probably equal to 0.1 omega. Otherwise, as far as the shape is concerned, is much better than the backward difference approximation. So it is quite clear from this comparison that for band pass filters, bilinear transformation is better. As far as the design of low pass filter is concerned, you can use any of the technique. For band pass and high pass, bilinear transformation is better, and also for the notch filter. So now let us solve an example of a high pass filter. In high pass filter, you know is as far as the transfer function is concerned, in low pass filter, if we inverse the terms containing s, for example, in low pass filter we had s upon omega c plus 1. Now reciprocal of that becomes a high pass filter, omega c upon s. Now it is high pass filter, right? So this is the frequency transformation. This is called frequency transformation. When you want to convert a low pass filter into a high pass filter, just substitute s by its reciprocal. So this transfer function is analog transfer function and representing a high pass filter having cutoff frequency 3 radian per second, and in this substitute the bilinear approximation, and after substitution and simplification you will get this transfer function h of z equal to 2z minus 1 upon 2 plus 3tz plus 3t minus 2. Now if we compare the magnitude responses of analog and bilinear transformation, the cutoff frequency is 3 radian per second and the shape of the magnitude response is exactly same as compared to analog filter. Now this is a very simple exercise problem for you. We have a band pass filter, and you have to convert this band pass filter using all three methods that we have discussed, and I would suggest you to compare the magnitude responses for different value of t in this using all three methods, so that you would have better understanding of these approximation methods. So that is end of the lecture number 23-24, and that is end of the course digital signal processing. And if you have any questions you can ask. My email address is given on the first slide of this lecture. Thank you very much.